as software library for modeling and simulation of solar desalination systems. www.reslibrary.com.
Hi everybody, Professor Muhammad Shah with you. Today we are going to talk about heat exchangers. What is the main concept? Briefly, what is the main types of heat exchangers? How can we run our model via this library? Let's go and see what we can do about this. Okay, a heat exchanger is a device used to transfer heat between two or more fluids. The fluids may be separated by a solid wall or tubes in order to prevent mixing, or they may be in direct contact in some cases. They are widely used in space heating, refrigeration, air conditioning, power stations, chemical plants, petrochemical plants, petroleum refineries, natural gas processings, nuclear power plants, and so on. It's widely used in thermal applications, especially in thermal application. The classic example of a heat exchanger is found in your car for an internal combustion engine, in which circulating fluid known as engine coolant or water through radiator coils and the air flows past the coils, which cools the coolant and heats the incoming air, and so on. This is a simple schematic about heat exchanging process between the coolant or water and coolant inside the engine, and the other fluid is going to be the air or air fans in order to cooling the water or the coolant through these tubes and fans and so on. Most of the common types of heat exchangers, the famous type is chill and tube heat exchanger. Chill and tube heat exchangers consist of series of tubes. One set of these tubes contains the fluid that must be either heated or cooled. The second fluid runs over the tubes that are being heated or cooled, so that it can either provide the heat or absorb heat required. Chill and tube exchangers are typically used for high temperature applications with pressure greater than 30 bars and temperature greater than 260. As you can see here in this schematic, this is the cooling side, supposed cooling side. A flow go from the bottom, and this is the exit side, and this is the hot side, another fluid. So as the coolant or the cooled side is going to absorb heat from the hot side and transfer heat or exchange heat between both sides. We have another type such as plate heat exchangers. These exchangers are composed of many thin, slightly separated plates that have very large surface areas and small fluid flow passages for heat transfer. That's the main advantage of such technique. There are many types of bound plate exchangers, such as depressed, vacuum, and welded plate varieties, and they are often specified for closed loop applications such as refrigeration, small desalination unit on ships or on the sea, something like this. We can categorize heat exchanger based on a number of transfer unit relations based on flow arrangement. We have barrel flow arrangement, counter flow, and chill and tubes cross flows, and you can use some correlations for this is a common correlation for all heat exchangers. Number of transfer units is it's a useful method in order to calculate the heat exchanger areas and operating conditions based on heat exchanger effectiveness and overall heat transfer coefficient. For parallel flow, you can use such configuration, such correlation. I'm sorry. This is suitable for counter flow and shell and tube parameters with number of passes. You can use these correlations, and this is common correlation for all heat exchangers. For parallel flow, as you can see here, we have inlet hot temperature stream as the same direction of inlet cooling stream temperature. Suppose we have X length of heat exchanger, we have entrance at 1, exit at 2, and therefore we have delta T1 between hot in and cold in, and delta T2 between hot out and cold out. For counter flow, a little bit different because we have to opposite the direction between the hot stream and the cold stream. Therefore, we will find that inlet hot stream will be in delta T1 without the cooling stream, and the opposite is correct. Therefore, this type of flow arrangement is quite interesting, and it has high effectiveness, relative high effectiveness if you are going to compare against parallel flow. For overall heat transfer coefficient, there's some standards. Suppose we are going to use water to water, water to water, water to oil. For example, for steam condenser, overall heat transfer coefficient normally between 1 up to 6 kilowatts per meter square degrees Celsius, something like this. You can use ammonia, tall wind. It's up to the user, because this model that we are going to talk about is simple, not complicated. There is no any use for integrators or transfer functions or something like this. It's simple. A user can add more working fluids, can add more types of heat exchanger, can transfer this model into a dynamic model by signal generator. You can use signal generator, and you can put inside the block of signal generator overall heat transfer coefficient, inlet hot temperature stream, inlet cold stream, and so on. In this model, actually, we are going to define some parameters because it's a design model. We are going to discover NTU. We are going to discover NTU and the area of the heat exchanger. Therefore, we have to assign or inlet hot stream, inlet cold stream, and we would like to discover outlet or calculate outlet hot stream and outlet cold stream based on some specific parameters you can address for. For such configuration, we have to study the effect of different working fluids. You can study the effect of operating conditions such as temperatures, what is the design aspects such as areas and overall heat transfer coefficients. Let's go and see what we can do about that. You have to go to your specific your location, your folder. Open your folder. You'll find this file. Double click on it. Okay, your model should be appear like this. Try to assign these reference model. Okay, everything is fine. Let's go. Double click on this block. As you can see here, we have here. You can choose between. This model is actually designed based on the flow arrangement. As you can see, you have to choose your flow arrangement. Suppose I'm going to select shear anti-tubes. Let's go for shear anti-tubes. Hit apply. Okay. Let's go inside. As you can see here, this is your model. This is overall heat transfer coefficient standards. You can use these values, and this is your correlations, and so on. We have here 4 flow arrangements: parallel, counter, cross flow, and shear and tube heat exchanger. We are going to talk about this one. Okay. let's see which parameters that we are going to assign. Yes, first of all, you have to assign your inlet cooling temperature. Suppose I'm going for 35 degrees Celsius for water stream, cooling stream. I'm going to sure, you have to choose between which working fluid you are going to deal with: air, heat transfer oil, water, ammonia. And sure, you can add in this model. It's up to the user. You know, user can edit and reform and add more, or asking for more working fluids, and we can add. It's simple. For hot side, I'm going to discover the effect of heat transfer oil. It's quite interesting. Heat transfer oil, operating temperature between 12 up to 427 against water from 0.01 up to degrees Celsius up to 300. Okay. For cooling side, inlet is 35. Outlet, I'm going for, suppose it's 200 degrees Celsius. Let's see. For effectiveness, let's go for normal. It's around 80% effectiveness. Mass flow rate, you can increase your mass flow rate as you would like, Okay, I'm choosing 2 versus 1. 2 for hot, 1 for cold, for example. Overall heat transfer coefficient, I think it's 110. Okay, for number of passes, you can choose your number of passes. Suppose it's 2 passes, 3 passes, but you can discover the passes by as a matrix. Suppose I'm going for from 1 up to 6 passes. I'm going to discover the behavior pass by pass. Okay, let's go. This is for dynamic. I'm going for single point run. Okay, we're going to run our model. Let's go for it. This is your model inside entire blocks, and you can discover specific capacity ratios, C minimum or C maximum. Outlet cooling stream, we're going to recognize thermal power of heat exchanger. Outlet hot stream, we're going to discover what is the area, heat transfer area of the heat exchanger, and number of transfer units. Okay, let's hit run. Okay, as you can see here, this is the area of heat exchanger based on your passes. This is 1 pass, 2 passes, 3 passes, and so on. This, if you have 6 passes for heat exchanger, sure, if you increase your passes, you will discover such effect on the heat exchanger area. What is the number of heat transfer unit? Sure, it's increased pass by pass, as you can see here. For inlet hot stream, if the inlet hot stream is 200, as we specified before, you will discover the outlet is around 68, because the inlet cooling water is around 35. I'm sorry. Yes, double click here. Yes, inlet 35 for cold, inlet for hot is 200. Yes, the outlet for cooling from 35 it's increased up to 67, almost doubled, and we decreased from 200 down to 68, nearly the same, because the efficiency of heat exchanger is 0.8. There is a thermal power heat rejection from the heat exchanger. It's 270. 0.5 and so on. Suppose you are going to discover the effect on the area by going dynamical. I mean, you can go here and select your signal builder. You can use this one, and you can control the inputs of your model by input temperature. You can use this model easily, or you can use the scopes and XY graph. You can discover many relation to each other and so on. I'm going dynamically. I will set our simulation time to infinity. Okay, let's go the effect. If you change some input parameter, I'm going here. Yes, let's go and check out. Okay, for example, yes, the effect on the area and number of transfer unit. If we change it as overall heat transfer coefficient, let's go and hit run. Okay, as you can see here, suppose we are going to change overall heat transfer. I'm going to increase, as you can see here, increasing heat transfer coefficient would decrease the area. Decreasing the area, I'm going to, yes, up to suppose it's 1000 watt per meter square. Okay, 1000. Okay, okay, 1080. Okay, let's stop our simulation. Let's see our run here. Sure, you can compare runs based on working flows. You can make one run and change your fluids and collect your data. If you compare, this is if you are going to compare runs, you can compare many runs, or you can compare the runs based on each heat exchanger. You can yes, this is the area, heat exchanger area. Suppose this is pass number 1, pass 2 passes, 3 passes, 4 passes, and so on. And this is number of transfer units. I'm sorry. Yes, this is 1 pass, 2 passes, 3, and so on. Okay. Okay. Suppose we are going to make another changes. Let's go here and see the effect of temperature, increasing or decreasing temperatures. Let's go here. Okay, let's hit run and see. Okay, now we are going to discover the effect of the area or the effect of temperature. Okay, let's go for temperature. Suppose I'm going to increase the outlet temperature. Inlet cooling temperature. As you can see, there is some effect of outlet cooling temperature, and sure, the exchanger area, I'm going to increase inlet cooling temperature. Yes, increasing. Okay, I'm going to decrease the heat exchanger effectiveness up down to 0.5, as you can see here. Okay, there's some effect on the area and at each pass, and the number of transfer units, as you can see here. I'm changing down to 0.5. Effectiveness is 50%. Suppose it's 50%. Okay, as you can see here, thermal power is decreased. Overall heat transfer coefficient decreasing. Okay. Let's stop. Let's see what we can do about that. As you can see here, you can collect your data. As you can see, I'm going to discover outlet hot stream temperature, outlet cooling stream temperature, thermal power decreasing, C minimum over C cold, and so on. It's quite interesting to discover many parameters. C minimum, this C minimum, This is C maximum, okay, C cold, okay, and so on. Okay, a simple model. There is no need for complications or something like this. You can reform it. You can add more working fluids. Also, you can add the signal builder block. You can control more inputs in order to discover overall heat transfer coefficient effect and number of transfer units, and many parameters you can handle. Anyway, we already had added this model, built this model because it's about fluid or flow arrangement. We can add more and more units. Don't forget to download waste gases cycles for thermal distillation processes. It's quite interesting for how to utilize waste gases with multi-stage flash and multi-effect distillation. Thank you for watching. Please support us with like, share, subscribe. Thank you very much.